Okay, today let's talk about the different system design problem designing a top K problem. So top K problem. So let's first dive into the functional requirements. Functional requirements. So basically, we will have a lot of events get into our system, and we want to be able to count the occurrence of all the events and provide some leaderboard of top K most popular events. Okay, let's say count the occurrence of events and provide a leaderboard of the most popular K events. All right. So this is our key functional requirements. Additionally, we would like to be able to search, perform search with so arbitrary, okay, interesting. Arbitrary, all right, time ranges, okay, all right. Okay, so we want to be able to search, for example, like in the past 1 hour, what's the most popular K events? And yeah, so that's something we want to be able to support. And let's say for the leaderboard, in the past day, what's the top K winners for a particular game or so. So yeah, those are the functional requirements. Come to the non-functional requirements. Okay. All right. So, okay. All right. So we want a fast reads. On so on, let's say, this is something interesting. So we so okay, let's first talk about the scalability. Okay, we want to support billions of events per day, and right, so billions of events per day means 10K, okay, per second. Okay, all right. And we wanted to have faster reads on So non-precise scenario. And we also want to support a precise solution. Non-precise, which provide approximation scenario. Okay. Basically, we want to support two separate scenarios. One is approximated, and for the approximated scenario, we want a faster read on them. However, for the precise solution, that's something we also want to check and support. However, it couldn't be as fast. This is a trade-off that we want to make, but we'll talk about this later. All right, so there's no not a lot of API discussion, and for the back of the envelope calculation, there's not much to discuss over here because we just get to know, okay, we have millions of events per day. That means we roughly need to support 10K events per second or so, and probably a peak at like double or triple the size. Definitely we need partitioning in this case. Okay. Okay. Let's talk about the so let's first talk about the precise solution. Okay, so flow. Let's talk about workflow. Okay, during workflow, we have a precise solution here, and we first talk about this precise solution. Okay, okay, let's say we have a bunch of events and we need to be listened to billions of events per day and 10K events per second. We will have a list of servers handling those traffic. So, and in order to apply a top K, so we could basically, so if we're resolving this via a algorithm, and we basically need to create a mean heap in each of the cluster in memory, and iterate each of the events coming up, and keep a key size of key mean heap for each cluster, and we could basically further merge all the key size mean heaps from all different nodes. So this is what we do. So the steps is that each cluster have a mean heap with size k. Iterate events, get top k per cluster, per node or so. Okay, so merge so merge values, merge k size mean heap for all nodes, and get top k. All right. All right. So this apparently this is giving us a like time okay time complexity O of let's say n log k um, on the first two steps. So each of the node will take O of n log k. N is all the number of events. K is the mean heap size of k. So right, and we also need to merge k. So we also need to merge everything from all the nodes. Okay, this is like the precise solution that we have. It's something like a map reduce process that is happening, and however, we also could trade the precision by speed. So we have approximation solution. Okay, so get, okay, so it's local. Okay. And okay, so also this is like a batch processing via like map reduce kind of thing. I mean, actually Spark map reduce. All right. However, if we could also leverage the streaming process. Streaming process. So that we can get the results much faster. Okay. However, the streaming, the events in the streaming system are not like the batch process. So because batch process have limited, have boundaries. However, streaming process have no boundaries. It's unbounded, like data. So let's say boundary with boundary, unbounded data. All right, so that's why we do need a window. So we do need to consider how do we want to leverage the windowing. So we could have a fixed size window or sliding window. And depending on what do we need. So let's say if we leverage each minute as the window, as a fixed window that we want to aggregate the data. So we could basically select window on 1 minute fixed size. All right. So let's say this is what we selected, and so what do we want to do with all the streamings? We could basically leverage the approximation method called count min sketch. So because we wanted to downsize our data volume to calculate So this is a algorithm that is a approximate algorithm, allows us to make count for the incoming elements in a certain window. So how does that work? So basically, it will have a bunch of hash functions. Let's say hash 1, hash function 2, hash function 3, etc. And we will have events like with the key of events like A, B, and C, let's say. Okay, so whenever the hash is coming, let's say we hash the key of A via all the hash functions. Let's say after hashing A, in the first one, A located on here. Okay. And after hashing like the second hash function, A actually locate here. And the third one, A actually locate here, let's say. Okay, then let's hash B. So okay, another event is coming and it's B, let's say. And this can be hashed after hashing. It might be over here. And after hashing via 2, the B might locate over here on the same blob as the A locate. So, however, on the third one, it might so locate somewhere over here like this. Okay, same for C. However, if we have a different event, A again come up, so A should be here and here and here. All right. And right, so let's say we have A coming up twice versus B come up just once. So how do we want to calculate? So we gather all the number in the all of the hash results. So let's take A, and we check this blob. It has 2, and we check this blob. It has 3, and we check this blob has 2. We get the mean value of this number. So that means we can A only occurrence of A is 2. However, occurrence of B is 1. So that's why we call it count mean sketch, because we are counting mean every time we want to count. So that represents how many occurrences comes up. Okay. This is just giving us estimation, because if A and B after hashing, they're having the like, so there might be some collisions, and for each of the blob, we might have C or D that give us a lot of uncertainty on the number, but that is just a small volume of data. And if we could basically well calculate the number of hash functions and the number of events coming up, and the number of keys that is potentially coming up, and there will be a math equation to calculate how many hash functions do we need to make the collision and the fault tolerant number to be as less as possible. So yeah, I don't want to cover a lot of math over here, but that's the rough idea of how the count mean sketch look like. And the main advantage of here is that we just need to keep these in memory. So these are string like matrix in memory, and it's a fixed number, so that our memory won't go crazily big while we are doing the calculation. So after, let's say after 1 minute window, we clean up the matrix, and we leverage the Flink node to calculate and dump to the next stage of our pipeline. And we can restart the matrix to get all the events from the next batch. So the next like a time window for the streaming data. So this is what the CountMe sketch and the approximation solution look like. All right. So what will our workflow look like? So basically, let's focusing on the workflow then. So we actually, let's say we have a like either client also, but it's not a user facing kind of a client. It's more like we just leverage this to be looking at the leaderboard service basically. So, and we will have, let's say, leaderboard. Service. But actually the leaderboard service can locate on the right side because let's focusing on how do we want to process the data first. Okay. First of all, we will have a event listener service. And so the service, okay, actually, I think it might be better to like organize my diagram like this. All right. Okay, basically it, let's say collect a bunch of events from the user side or so. Oops. I'm not actually pointing to, okay. Yeah, like the events coming up to the event listener service. And we will have a Kafka, and let's say, all right. How should we do this? Streaming, okay. And also we wanted to have a bunch of count in sketch node. So let's listen to Kafka, and this is listening to Kafka. Okay, and the event listener is producing data to Kafka basically. Okay, let's here. So the count mean sketch is basically loading all the data to S3 or so after count mean, it actually is going to populate data for each of the time window for every minute, and we want to store those types of data as potentially the raw data. So, and let's say first we want to dump to S3. Okay, so raw data is coming to S3, and the count mean node. We also leverage Flink or Spark as well to do that kind of work, and we could yeah, so dumped it into, so maybe not S3. So I think OLAP DB. So it's normally some column-wise database, easier for query. And so from the Spark streaming side, it needs two steps. Basically, for all the nodes, like after partitioning, for all the nodes that keeps a mean heap for each of the cluster, it needs to go to a aggregation service. So we also do this via Kafka. So let's see. All right, we want to chain this process, and let's say we have a bunch of Kafka streaming, and it basically calculate from each. So it basically calculate from each each node of the top K, and like we aggregate right after and we get merge all the top K from each node and get the global top K. So after getting the global ones, we will also land of the data to the OLAPS database. All right, over here, basically we have two flows like over here. So this is much faster, and let's say, so we might leverage Flink, let's say, and this can also be a Flink node by working on the count mean sketch. Keep a copy of the hash functions, and the matrix collecting every minute of it. And we definitely flows everything into the OLAPS database, and we will so also we could also leverage like time series DB, because this is more like a time series. So right, but yeah, OLAPS database is another choice. Okay, on the OLAPS database, we also have certain, so how should I draw this diagram? Okay. So since we already get minute level data, so we could leverage multiple copies. Let's say 1 hour data. Three-hour window data, and potentially daily data. Okay, so we will have different copies of data. So allowing us, so it's generated from the minute data. And we, so in order to allow the leaderboard to query different, with different time window, so we could utilize multiple different derived copies for the data to achieve this. Okay. Yeah, so actually, potentially the client could be also a event contributor. So it depends on the case. So how many likes, let's say, if the client itself could be an event source, and it could look at the leader service to query in the past hour who's the winner, and in the past day who's the winner. It depends on what we want to show to the client. So, and like the storage, could be either OLAP database or any Parquet file or time series database, all different types of database that is helping us for the leaderboard service. So, however, as the time goes, for example, like 1 year ago, we don't need to care about the leader information, the ranking information within 1 hour's window. So as the time goes, we truncate all those data granularly, and we just keep, let's say in the past day, we only care about 1 hour. We don't care about a minute window anymore. So after a year, we only care about the daily throughput instead of hourly. So we gradually move all the data to the cold storage, like AWS Glacier for cheap storage, those cheap storage solution, and we don't query that often. And we dumped more granularity data to the Glacier first, and gradually dumped all the other 3 hours of kind of things. So, all right, let's get back to all the requirements, make sure we have everything covered. Functional requirements, we want to count the occurrence of events, provide a leaderboard for the most popular key events. And yeah, this is it has been covered, and we want to perform the search with the arbitrary time range. So in order to make this fast, we have different copies of we have a basically couple of copies of the minute level data to the hour, 3 hours or daily. Even with the 2 hours, let's say we can always quickly query the 1 hour database to aggregate 2 hours out of one per hour. So that makes things super fast. And because we only care about the top K popular events, all the dump over here could just be K. So that saves us a lot of memory. We don't want to keep everything, all the events that is happening in that hour, because that will be a lot. Because we're deriving data with multiple copies, that needs a lot of storage. We don't want to do that. In order to save the cost, we just keep the top K events because that's something we care about. So we can also dump them into cache for like the past hour. For the frequent leverage the queries, so we can leverage AI, machine learning, to tell us what's the most frequently used query from the user, so that we can store that copy to cache. Depends on our query patterns. Most frequent query the result. We can pre-populate those data into the cache so that leaderboard can quickly fetch those from the cache instead. All right, we want to support billions of events. This is definitely supporting that, and fast read on approximated scenario. So for the approximated scenario, we're actually flowing the event listener service, flow the data into CountMean Sketch. So CountMean Sketch directly dump the data to the DB and allow the leaderboard to query. So for that minute or hour. So like more extremely, if we really care about that particular time window, we can either let the CountMean Sketch node to update the, maybe not, because we also need some gathering on top of it. But so yeah, so basically we do need some query service over here because we have multiple copies for the node and for different partitions. Okay. All right. Basically, we so let's talk about how do we want to partition our data. Okay. So for Kafka, we definitely want to partition by event ID. Okay, I think yeah, it makes sense. And like Flink and this CountMean Sketch node is also partitioning via the event ID. And so the aggregation service is actually looking for all the nodes from the Flink and dumped into the like the query database over here. And right, so yeah, I think that's the partition I want to mainly covering. In order to make everything fault tolerant, and I think we could always have a replication for each of the node over here. Actually, Flink already is supporting that functionality, and Kafka is also having replication. So over there, a replication is helping us to make it high available and fault tolerant. Um, right. So I think that's what that's all I want to cover. So very last thing. So I think over here we wanted to dump the raw data to S3 to keep storage, and we might want to run Spark job offline to check if to do the reconciliation to see if our results are accurate or having a lot of discrepancy over there. So yeah, so I think that's it. Thank you very much.